All right, so I want to work through a couple more examples here and really get down this process of what we're looking for. One thing that you do need to understand is that you're not necessarily going to be given this list of stuff that you have to fill in, okay? I'm listing all these things because these are possibilities. You may or may not need all of them. You may not have all of them. As we'll see in this example, we actually, a number of these things don't really apply, okay? So let's take a quick look here at example 1. I'll also say this, I'm not going to be using the table for every one of these. I prefer to just use sign diagrams. If you like using the table, go for it, okay? But it's down there if you want it. Okay, so let's look at our function. We've got f of x equals x to the fourth minus 12x cubed plus 48x squared minus 64x. So immediately, what do you see? What do you know about this function?
It goes through the origin.
It's a polynomial. It goes through the origin because...
Every zero
doesn't have an intercept.
Yeah, okay, so there we actually know our y-intercept is 0, 0. And we actually know that one of the x-intercepts is going to be 0, 0 as well. Okay? It's a polynomial, so what does that tell us?
It's continuous.
It's continuous everywhere. It's differentiable everywhere.
There's no asymptotes.
Okay, we could have multiple zeros. We could have up to 4 different zeros or x-intercepts here.
No horizontal. No asymptotes.
Okay, no asymptotes. It's continuous everywhere, so that's kind of nice. There are no vertical asymptotes. There are no horizontal asymptotes. It's continuous everywhere, so our domain is all real numbers.
So it goes to negative infinity and positive infinity?
Yes, it is going to. Now let's think about our end behavior. Our end behavior...
It's going to increase without bound. Like,
Yeah.
Okay.
It's going to increase both ways to negative infinity and to positive infinity.
Yeah, there we go. This is a positive x to the fourth. So the positive tells us what the right side does. Positive says the right side of this polynomial is going to go up forever. The fact that it's an even degree tells us the left side does the same thing as the right. So I know it's going to go up to the left as well. Now, I don't know what goes on in the middle, but I know the two ends are doing those things. The end behavior, positive 1, means it's going up to the right. Positive, up to the right. Even degree means the left does the same thing. Okay? Yes?
So, for our x-intercepts, our y-intercepts, we have points, and then our asymptotes, we have none. For end behavior, how would we denote like what's actually going on? What would...
End behavior is really just an observation.
Okay.
Okay? Or if they asked you, hey, what's the limit as x approaches infinity?
Right.
We'd say, hey, it's approaching positive infinity, so the limit doesn't exist.
Okay.
You know? So that's almost more of an observation. That's why I just drew like the little horns. Okay? Now, let's finish off our x-intercepts because there's more than just 0, 0, or there's up to 4 of them. So let's deal with this. This one gets kind of fun. All right? I pull out the common factor of x. That's what gave us 0.
Yeah.
And I've got x cubed minus 12x squared plus 48x minus 64. So I want to figure out where does this equal 0? Okay?
Oh, there's 0.
Where does it equal 0? Because I'm trying to find x-intercepts, all right?
Just set that part equal to 0.
Yeah, okay, so I've got this cubic part in the middle equal to 0. So how am I going to figure out where that equals 0? Okay.
Then
And then you square
Okay, so if we can factor out something and get a quadratic, we can use quadratic formula for the rest of it. We gotta factor something out. Now when you have a cubic, what should you probably try first?
X.
0? No.
Well, hang on, what method should you probably try first?
Factoring.
Factoring by grouping, okay? Now this one here, unfortunately, if I factor it by grouping, I'm gonna get x squared times x minus 12 plus, and I could take out a 16, and it's a 3x minus 4. These are not the same thing, so factoring by grouping isn't gonna work here. Okay? Unfortunately, we're going to have to do something else. Now, how do we factor out something if it doesn't work that way?
Synthetic division.
Ah, there we go. You remember your rational zero test?
Yeah.
I don't.
So we got to get factors of 64, negative 64.
Oh, it's like P and Q and Q.
Yeah, the P's and Q's thing, right?
But wait, is the P the first, like, coefficient, or is Q?
Which one goes on top?
Yeah, P.
Factors of 64.
Factors of the end.
Oh, so
Okay.
P's the N and then Q's the.
If the P's and Q's are confusing, don't worry about it. It's the factors of the constant over the factors of the leading coefficient. And they were really nice to us. They gave us a 1 as our leading coefficient.
Yep.
So, we got 1 in 64, 2 in 32, 3 doesn't work, 4 in 16 works, 5 doesn't work, 6 doesn't work, 7 doesn't work, 8 times 8. And guess what? Since these met in the middle, I know I've got all of them. Okay?
It would also be plus or minus, right?
What do you mean?
Yeah. Now, it does mean plus or minus, okay?
Yeah.
So all of these guys are plus or minus. Okay? Now, we're going to have to do our synthetic division here. I put the coefficients, 1, negative 12, 48, negative 64. And I just try stuff. I usually start with 1. Okay? If I try with 1, I bring down, I multiply over. I add down, I multiply over. I add down, I multiply over, and that does not equal 0. So I know that that will not work. Okay? Now, I'm going to just jump to the end here because I already know the answer, and I don't feel like spending half our class time trying all these things.
What I mean is we will have to try it.
Okay.
Judge which numbers kind of even look like they're going to work versus which numbers don't look like.
Yeah, you could take an educated guess, and I'll take an educated guess of 4 here. Okay?
Yeah.
So, because I know it's going to work. Alright, if I add down, I have 1 times 4 is 4. Add down, you get negative 8 times 4 is a negative 32. Add down, and I get 16 times 4 is 64. And I get 0. And what do you know? There's a good guess. Alright, so, yeah, here's the nice thing. You got to know what you're given. You got to know what you just found. Alright? It does no good to do this if it doesn't tell, if you don't know what the results mean. So now I know that this thing is x times x minus 4.
X squared minus 8x plus 16.
There you go, okay? So, remember, the top here, this was x cubed, x squared, x, and the number. On the bottom, I lose a power, okay? Guys, please stop the conversations, alright?
Why is it X 4 minus? No.
Hang on. I'm losing a power because I'm dividing by an x. So instead of x cubed, this is the x squared, this is the x to the first, this is the constant, and this was our remainder. We needed it to be 0 to make sure it came out evenly. Okay? So now I've got that factored, and now I know my x-intercepts are at 0 and 4.
You can factor it out.
And what does that factor into?
Yeah, x minus 4.
Yeah, I've got another x minus 4 squared, so that whole thing actually just ends up being cubed.
Duplicity.
Okay? So, now I know my x-intercepts are at 0, 0, and 4, 0. And that has a multiplicity of 3, which means it's going to level off but then continue to go up, if you remember from last year's stuff. Okay? So let's graph what we know so far. What I know so far is I've got a point here, and 1, 2, 3, 4. I've got a point here. Okay? So let's use our first and second derivatives to help us figure out the rest of this, okay? Because I want to figure out critical numbers, increasing and decreasing, also concavity.
So 4 is the only axis or something? And 0?
4 and 0, those are the only two. Remember the degree of 4 means we can have up to 4.
Up to 4.
Yeah.
Not 4.
You could have 4.
Yeah, I mean, not 4.
Yeah, not necessarily 4. In this case we got a triple root, so. Alright, so first derivative.
4x cubed
4x cubed.
minus 36x squared
Good.
plus 96x minus 64.
Alright. Okay, so we've got this.
Finding derivative is easier than simplifying it.
Yeah, finding the derivative is a little bit easier. Now, here's one thing that that we can try. I want to find where this equals 0 to get critical numbers.
So you just have to find when 4x cubed minus 36x squared plus 96x equals 64.
Well, yeah, but we want to keep it equal to 0 here, because if we're going to try to factor or anything,
Are we doing the P's and Q's again?
yeah, we're going to do the P's and Q's. But think, x minus 3, or I'm sorry, x minus 4 cubed was a triple root. And if you think about what that's going to look like on the graph, I know a triple root, I come up and I approach and I level off and then I continue to go up.
So that's a plateau point?
So chances are that's going to be I think it at least is going to be a plateau point. So that means x minus 4 is a root of this equation as well. So let's try it. X minus 4, and then if I do the synthetic division, I'll have a quadratic left over. So 4, negative 36, 96, and negative 64. I throw a 4 in here. 4, 16, negative 20, negative 80, 16, 64, 0. Alright, so I've got a 4x squared minus 20x plus 16.
So it could have not worked.
If it hadn't worked, then I probably did something wrong.
So you always.
Okay. Maybe, because we had a triple root in the first one, I was figuring it would work here.
So why wouldn't it work?
I don't know. I mean, in this case, I knew it was going to work because I knew triple roots always ended up being a leveling off point, so I knew the derivative would equal 0 there. Okay.
Oh,
Now,
okay.
the other thing I can do here is I can factor out a 4. Okay, I'm going to factor out a 4 of all of these, just to get my numbers to be smaller. So there's a 4, and that's going to be an x squared minus 5x plus 4. And that's helpful because I know how to factor that now.
Oh, that's.
Okay? That's an x minus 4 times an x minus 1. So I have a 4 times an x minus 4 times another x minus 4 times an x minus 1. So what are my critical numbers?
1 and 4.
Yeah, 1 and 4. Okay? So those are my critical numbers at x equals 1 and x equals 4. So now I'm going to do my sign diagram. 1 and 4. My first derivative, and what's my function doing? Okay? So if I plug in a 0 into my first derivative, I get a negative number. So I know that the function was decreasing as I approach 1. If I plug in, say, a 2 between 1 and 4, I have to do a little bit of arithmetic, but I can use the factored form to help me out. Okay? The factored form, 2 minus 4 squared is positive, 2 minus 1 is positive, so that's all going to be positive. And then if I plug in something bigger than 4, like a 5, I get a positive and a positive as well. So that confirms my thought that number 4, at 4 we had a plateau point. Okay? But it also shows us that at 1 we have a min. So the min is at 1, and if I plug that into the original function, I have 1 minus 12 plus 48 minus 64. So let's see, a negative 76 plus 48 is a negative 28, plus 1 is negative 27. Okay? So that's going to be my min point. The plateau is at 4, 0. Okay? It's not an asymptote, it's just it actually is defined there at 4, 0. Okay? So I put my min point way down here at 1, negative 27. And this goes all the way down to here. I know I hit the point 0, 0. And you can actually see what's going on here. You can see what we figured earlier about the fact that, you know, this would be a plateau. Okay. So I have my min, I have my my plateau point. We can also identify intervals where it's decreasing and increasing. But the last step here is I want to go ahead and find our second derivative because I want to identify areas of concavity. Okay? So I'm going to take my first derivative and take its derivative, f double prime of x, and I get a 12x squared minus 72x plus 96. And if I set that equal to 0, I'm going to divide everything by 12 first of all. So that'll make life a lot easier. X squared minus 6x plus 8. And I can factor that, x minus 2 and x minus 4. Okay? Now, because 4 was a plateau point, I knew it was going to be a point of inflection as well. Alright? But here we kind of confirm that idea. X equals 2 and 4 are possible points of inflection. If I do a sign diagram there, my second derivative, if I plug in 0, I get a positive 96, so I know I'm concave up. Which actually I knew because I had a min at 1, and 1 is in that range. So I knew the second derivative had to be positive for it to be a min. If I plug in a 3, I get 1 times a negative 1. So that's negative, it's concave down.
Yes.
And then at 4, or at 5, I'd have a positive and positive, so it's switching to concave up. So I do have 2 points of inflection. Points of inflection. Two something, and I know 4 is 0. Okay?
And you can just plug it into the original equation.
Yeah, if I plug 2 into the original equation, I have 16 minus 96. So negative 80 plus 4 times 48 is 160, 192. 192 minus 80 is 112. Minus 128 is a negative 16. Alright, so I know at 2 I'm at negative 16. So that point right there is where our concavity changes. Okay? So that's what our graph looks like. We can confirm that by looking at it down here. Okay? We can find all of that and identify all the different features by hand. Notice there's a lot of pre-calc honors stuff getting tied in here. The synthetic division, rational zero test, all that kind of stuff. Okay? So keep reviewing. Come in for help if you're looking at that and you're like, I have no idea what you were doing there. Come on in and talk. Okay? So example 2, we're going to sketch cosine over 1 plus sine. And let's start, first of all, thinking through, are there any of these features that we can find before we do any actual calculus?
Domain restriction. What is this?
Well, yeah, domain.
Okay. Okay, domain. So what is our domain going to be?
X can't be pi over 2 or 3 pi over 2.
Okay, and why is that?
Because that makes
Okay, so sine cannot be negative 1, right?
yeah.
Okay, so let's think through this here.
It's not pi over 2.
The domain,
3 pi over 2. Just 3.
Sines.
It's definitely 3 pi over
Pi over 2.
Yeah, just pi over 2.
No, it's
Just
definitely
3
3
pi
pi
over
over 2.
yeah, sine of x cannot be a negative 1, so x cannot be 3 pi over 2 or any coterminal angle with that. So we could do a plus 2 pi n. You know, any multiple of 2 pi added to that, it will not be in the domain either. Okay? So that's the first thing. And by the way, are those going to be holes or asymptotes? Yeah, those are actually going to be asymptotes, all right, because they're not going to cancel out. So actually, this vertical asymptote and the domain restriction, okay, would be will end up being very similar. All right, so the vertical asymptotes are x equals 3 pi over 2 plus 2 pi n, where n is any integer. Okay, n is any integer.
What is that symbol?
That's the z for integers. N is an element of the integers. We saw that before. Okay? The domain restriction is basically this, but it can't equal that. Alright? The domain is x cannot equal 3 pi over 2 plus 2 pi n. Alright, so that's the first thing. What else can we find without having to plug in, or without having to do any calculus? Intercepts, okay. So x-intercepts, where are those going to be?
When y is 0.
When y is 0, so this whole fraction has to equal 0. So that means, yeah, the top has to be 0, cosine has to be 0.
Pi over 2. Pi
Okay.
over 2.
So cosine x equals 0. X is at pi over 2 and 3 pi over 2. However, can't be 3 pi over 2 because that's not in our domain, right? So the x-intercepts are going to be at pi over 2, 0, and also any coterminal angle. So I'm going to put a plus 2 pi in there, 2 pi n in there as well. Okay, so we got a bunch of plus 2 pi n's in this problem here.
Y-intercept is
Okay.
0.
Alright, so y-intercept, we plug in 0 for x,
Oh wait.
cosine of 0 is 1, sine of 0 is 0, 1 over 1 is 1. Okay?
Period. I don't remember how to find the period.
Alright, now,
Wasn't it like something over B?
2 pi over
Negative
2 pi over b,
or 2 pi over
We have to know what type of graph it is. This is
How
like,
do you know it's
yeah, it's not a
Okay.
cosine or a sine graph, it's together.
it's not a cosine graph or a sine graph, it is together, but what's the period of cosine x?
2 pi.
What's the period of sine x?
Pi. Wait,
2
I-
pi.
2 pi, yeah.
So since they both have the same, then when we find the ratio of them, the ratio is also going to have the same period as well. So the period is going to be 2 pi.
Wait, so what are the two, so the period of sine is 2 pi and the period of cosine is just,
Is 2 pi.
oh,
Because there is no shifts, right?
Because they're the same. There's no shift, there's no coefficient in front of the x's, so that doesn't, remember, that's what changes our period.
So B is the coefficient of the x.
Yes,
What's the equation defines the period again?
2 pi over b. And like Dana just said, the b is the coefficient in front of the x, or the angle. Okay?
and there's no coefficient, or just one.
It's 1, yeah. So, alright, so horizontal asymptote,
Tan? Cotan?
there's not really, I mean, cosine over sine, think of it, it says end behavior, okay, but cosine over sine would be cotangent, and we know that goes from negative infinity to infinity. So even if we were adding the 1 to the denominator, that's not going to do anything, alright, so,
Would it be better if we
so we're not going to have any horizontal asymptotes here.
could you also rewrite it as cosine plus cotan? Because it's cosine over 1 plus sine, which means it's cosine over 1.
Well,
Oh
no.
no, never mind.
If this were flipped, you could split
Yeah,
it into
never
2
mind.
separate fractions, but you can't do that here.
Goofy.
Alright, so now we need to actually do some calculus, alright? And we'll kind of see if there's any symmetry at the end. If I plug in a negative x, cosine of a negative x is same as cosine of x. However, cosine of sine of x is not the same, so it's not going to be symmetrical that way. So we'll see if there's any other kind of symmetry. But let's go ahead and actually graph what we have first, and then we'll do the calculus. Okay? So we have x-intercepts at pi over 2. There's pi over 2, here's pi, here's 3 pi over 2, and here's 2 pi. I'll stop there for now. And we'll also go to the left, negative pi over 2, negative pi, negative 3 pi over 2, and a negative 2 pi. So this says that we have x-intercepts at pi over 2 and then every coterminal angle. Alright, so x-intercept here. And then if I go forward a period, that's going to put me over here. If I go backwards a period, it's going to put me here. Okay, so there's 3 x-intercepts. The y-intercept is going to be at 0, 1, so we'll go ahead and put that right there. And then I've got asymptotes, vertical asymptotes at 3 pi over 2. And then if I go back 2 pi, I'll have another one here. I could go back another 2 pi, and I'd have another one over here. Okay. So you see our graph starting to take shape here.
It looks like a tangent, kind of.
It does kind of look like a tangent or a cotangent. Alright, so let's go ahead and start looking at our first and second derivatives. Okay, so first derivative, f prime of x, let's zoom in over here. Derivative of the top, negative sine x times the bottom minus the top times the derivative of the bottom, which is just cosine, all over 1 plus sine x squared.
So
Okay.
cancel out that,
So I'm going to have, let's see, a negative sine x minus sine squared minus cosine squared. Over 1 plus sine x squared. Now, what can I do at the top to make that look a lot simpler?
negative.
Okay, what with a 1?
Sine squared and cosine squared.
Okay, sine squared plus cosine squared equals 1. So I'm going to factor a negative 1 out of those two terms and make that a plus sine squared and a plus cosine squared. So now I have a negative sine x minus 1 on the top. Okay, my Pythagorean identity.
You can factor out the negative again, right?
Oh, we could, yeah.
So you could cancel out the bottom 1.
Yeah, we could. 1 plus sine x. Let's do this step here first, and then we can show what Daniel's talking about. He said now we have this, and then if I factor out the negative from this, I have a negative 1 on top, and it canceled out one of those square on the bottom. Okay? So that cancels out one of those, and I have a negative 1 over 1 plus sine x. Now, question, where does this equal 0?
It doesn't.
Nowhere. Nowhere. Okay? So this never equals 0.
So it never crosses 0? So
Well, it means we don't have any relative max or min points on this whole graph, which may seem kind of weird until you see it eventually.
But it's a cotangent.
It's gonna be like a.
Okay? It does look kind of like a cotangent graph, so actually that's what ends up happening.
So it's going to be just going down all the time because tangent is going out, so this one is going down.
Okay, yes. Now, check this out. This is where the other part of this comes in. Where is f prime undefined?
Pi over 2. Or 3 pi over 2.
Yeah, when sine x equals negative 1. Well, that's 3 pi over 2
So that's the limit.
plus 2 pi n, okay? Well, look, 3 pi over 2 plus 2 pi n, those were our asymptotes, right? Which makes sense here. Remember we said you would put asymptotes on your sine diagram anyways. Okay, so if I'm doing a sine diagram for f prime, and I have a, a 3 pi over 2 here, I have a negative pi over 2, excuse me, and I could go the other direction as well. That would be 7 pi over 2, and so forth. Notice, no matter what I plug in to the derivative, okay, I'm going to have a negative 1 over 1 plus sine. Now, if sine is positive, I have a negative 1 over a positive, right? If sine is 0, I have a negative 1 over 1, which is negative. And if sine is negative, the biggest it will ever be is negative 1, right? And that's where the asymptote is. So no matter what I plug in here, my derivative is going to be negative on all of these intervals. Now, I don't have a bunch of plateaus, I have a bunch of asymptotes. And that's why this thing here is going to look like this, okay? I can sketch it before I even get the rest of the information here. Notice it's decreasing for the entire domain. Okay? That's what that would look like.
So, is that just a coincidence that we had cosine over sine and it's a cotan, even though it's 1 plus sine?
No, it's not a coincidence. It's a slightly modified version of it. Okay?
So we did kind of know what it was going to look like.
Yeah. Yeah, if you were thinking about it, you kind of knew what it was going to look like to some degree. Now, let's go ahead and also look at our second derivative and tell what we can about it, about that. Okay, so I'm going to use this fully simplified version, the negative 1 over 1 plus sine, and I'm actually going to rewrite it as, okay, f prime of x is a 1 plus sine x to the negative 1. That way I can use chain instead of,
Does it need to be negative?
Yeah, it needs
oh
to be
yeah, negative that. Okay? So what I'll do for the second derivative is the chain rule. So negative 1 times negative 1 is 1 times 1 plus sine x to the negative 2 times cosine x. Okay? So that gives me a cosine x over a 1 plus sine x squared.
Can you distribute the square? And make it
You'd have to FOIL.
Yucky.
So where does this equal 0?
Cosine is 0.
When cosine is 0. Now that sounds familiar because those were also our x-intercepts.
And that's where it changes concavity.
And that's where it changes concavity. Yeah. Okay? So points of inflection are where cosine x equals 0. Those were the x-intercepts that we found before. So hey, there's a point of inflection, point of inflection, point of inflection. Okay? To double check that, we can actually do a sine diagram. Here's our pi over 2, negative 3 pi over 2. We had a, what would that be, a 5 pi over 2. Okay, our second derivative, if I plug in, say, a 0, I'll get a 0, or I'll get a 1 over 1 squared, so that's a positive. If I plug in, say, a pi, okay, cosine of pi is negative 1. Negative 1 over something squared is going to be negative. Okay, and we'll end up seeing a pattern here. Okay, so where it's concave down, then concave up, then concave down, then concave up, and you can see here, guys, we have our intervals of concavity. Now,
Can you show where?
one last thing here real quick, sorry. The one thing I left off of here were the points where it is undefined. Okay? So actually, the negative pi over 2 should be in there as well. And also the 3 pi over 2 and the 7 pi over 2. But notice there, the concavity's not changing. Or I'm sorry, yeah, the concavity would change. Sorry about that. I got ahead of myself a little bit. Okay. Let's fix that real quick. Okay, so we have negative, then positive, negative, then positive, negative, then positive, then negative. Okay, and you can see here from a negative 3 pi over 2 to this was a negative pi over 2. Right here, it is concave down. All right.
But isn't it, when will it be concave up?
It's concave up. Hang on. Right here. This was concave down. This is concave up. This is concave down. Concave up.
Can you show it on the graph?
Concave down. Concave up. So here, concave up. Concave down. Concave up. Concave down. Concave up. Concave down.